Okay, enough for now about spanning tree history and background. Now we jump into graph theory. Yes, again, as we did for OSPF. Why? Because it's a great math tool to represent networks and to understand what's happening under the hood of these kind of protocols like spanning tree. So just a brief recap what a graph is. A graph is a graphical representation of relationships, where we say that the entities that are somehow related are called nodes or vertices, and the things that link them together are called edges. Why this is useful for networks? Because we can think of the nodes or vertices as network devices like router switches or any other network device, and the links between them like cables, circuits, or whatever we have as the edges linking them together. So here in the example, we have three different graphs made of, all of them made of four nodes, but in this case you have four edges. Here we have 5 edges, and here we have 6 edges. If we see the definition, the spanning tree of a graph of n vertices, and in our case is 4, is a subset, so it's like a smaller part of n minus 1 edges. So if we have 4 vertices or 4 nodes, we're going to have 3 edges that form a tree. So if you see here, the interesting thing is that we have different spanning trees, right, from the same graph. And the important thing is that in all cases, all the nodes are somehow reachable, right, through the tree. Okay, so this is very interesting and very important. If we move forward, we have another definition, which I think it's also clarifies a lot. So spanning tree is a connected graph, as we saw, using all vertices in which there are no circuits. So there is no way from one node to take a tree path and come again to the same node, right? So it's always going to an end for all edges. So it's just, in other words, there is a path to any vertex, to any other vertex. Vertex is also called, as we call, nodes or vertices, but no circuits. Again, I don't have loops, and that's where the spanning tree comes into place. And last but not least, about the graph theory and why this is useful for our spanning tree discussion is that we can discuss about the minimum cost spanning tree. So now I not only have a graph, but I also have like a graph that has costs to reach one node to the other. Same somehow as we discussed for OSPF, but now for spanning tree. And I want somehow to calculate which is the best path or the best tree, the best spanning tree to reach each of the nodes. But contrary to OSPF, I don't want loops. I just want to reach all of the nodes, but without making any circuits. So here we have an example. In this case, the example is made with like money. If we can think of this like roads and different cities or maybe different corners of streets or whatever, and this would be the minimum cost spanning tree to reach all of the nodes, but again, without making any kind of loops. Okay, guys, last 30 slide before we jump into the labs. So in this case, this is a huge table, but I'm trying to summarize or squeeze in all the flavors and evolution of spanning tree for almost the last 35 years, more or less. So here we start with spanning tree, the regular spanning tree, the 802.1d, which is also called, it has only one instance, a common spanning tree. That this basically means that on my physical infrastructure, I'm going to calculate a spanning tree as we saw before, and that's going to be my topology for all, basically for everything that is running on my network. Then Cisco came up with this per VLAN flavor, which basically means that I can calculate different spanning trees per VLAN. Let me try to illustrate this real quick with an example here. So let's suppose I'm going to draw real quick a typical topology we can see in our networks, in campus networks or data center, or maybe a small data center as well. So let's suppose this is our core switch 1. It's going to be our core switch 2. This is going to be our access switch 1. This is going to be our access switch 2. And we usually have dual home connections if at all possible. Something like this. Every access switch is going to be dual home to our core switches. And usually we're going to have a connection like this, right? So again, if we are running the simple spanning tree, I'm going to have a single a single topology, right, that is going to be active. Let's suppose for access switch 1, the loop is going to be like this. So let's suppose that this link becomes blocked. And the forwarding link is going to be this one. And for access switch 2, let's suppose that, I don't know, maybe because of some cost or whatever calculations, this link became blocking, and this is forwarding, right? So this is how the network or the spanning tree converge, and we have only single spanning tree here for only topology. However, let's suppose that I have several VLANs and I'm running per VLAN spanning tree. So this is what it could happen. So let's suppose we have, let's say, let's put it black here. So I have VLAN, or I'm going to use like blue. Let's suppose I have here VLAN 100 for, let's say, data, VLAN 200, let's say, for, let's say, wireless. Let's suppose then I'm using VLAN 300 for voice, and VLAN, I don't know, 400 for a DMZ. Let's suppose we have a firewall somewhere, and we have a DMZ somewhere. Okay, so in this particular case, the per VLAN spanning tree may calculate different spanning trees depending on the VLAN, right? So let's suppose that for VLAN 100, spanning tree calculated that this link over here is going to be blocked. And for access switch 2, let's suppose that this link over here is going to be blocked, right? So the path that the traffic is going to take for VLAN 100 would be this link and this link, right? But for, let's suppose, VLAN 300, maybe a different spanning tree can be calculated. So let's suppose that in this case, the same. In the case for access switch 2, it's blocked here, but we could think that for access switch 1, this link is blocked. So in the case of VLAN 300, the path, the traffic is going to take this path, and is going to take for access switch 2 this path over here. So you see, we have calculated different links that are going to be forwarding or blocked depending on the VLAN, and we can have several different spanning trees calculated per VLAN on the same physical infrastructure. That's what it means for the per VLAN spanning tree. Then moving forward, we have, well, the difference between spanning tree, the classical and the per VLAN spanning tree plus, that has to be with Cisco, that came up with the 802.1q trunks. Before, this was a legacy protocol, the ISL, a legacy trunk protocol. But usually this is not longer in use. So if we are using trunks with 802.1q, most sure we're using per VLAN spanning tree plus. The same happens with Rapid and Rapid spanning tree plus. The difference again is that Rapid spanning tree has one single common spanning tree, so it's the same, only one spanning tree calculated for the topology. In the per VLAN, we're going to have one spanning tree calculated per VLAN. And MST is kind of a mix of the two, right? Of having just a single common spanning tree or having per VLANs. We say, okay, I have a physical infrastructure. It maybe doesn't make sense to calculate the spanning tree per VLAN, because if I have 1,000 VLANs, I'm going to calculate 1,000 spanning trees, right? So MST says, okay, let's create maybe 2 instances, right? 2, 3, depending on your infrastructure, but let's suppose 2. I put all my VLANs or my odd VLANs in instance 1, or my even VLANs in instance 2. And that basically means that I'm going to calculate only 2 spanning trees and group all my VLANs, right, in only those spanning trees. So that's kind of, saving resources, and at the end of the day, the network's going to behave the same. Then we have here the port roles, link types, and the features. Basically, if you read about port fast, uplink fast, and backbone fast, these features were basically added to the newer flavors of Rapid Spine 3 and MST. Basically, the port fast now became part of, there with maybe some minor differences, but the features that were port fast, uplink fast, and backbone fast became part of the standard as edge link type, alternate port roles, and accepting inferior BPDUs in the case of a link failure that is not directly connected. So, well, I hope this table can help you, that try to summarize or put together all the different flavors and the evolution of the spine protocol.